Good morning. I hope you will look at me, not the computer screens, but let's see how it goes. My name is Payam Barnaghi. I work at the University of Surrey. Also, I coordinate a European project on smart cities and data analytics, which is called CityPulse. How this works. You see the logo here. Today I'm going to talk about semantic technologies for Internet of Things. Before I start, how many of you are familiar with semantic technologies? One? I'm sure there are a few more, but maybe you're shy. Yeah, there we go. Three, yeah, see, I'm sure there are a few more, but when I say semantic technologies, if you're going to design a semantic technologies, what do you do? Let's ask this gentleman. See, you volunteered, and now you've got to answer questions.
Define something to describe objects or stuff in a standard way.
Yeah, we are trying to describe object things in a standard way. Do we have an idea what that standard way is going to look like, or what tools we use? Have you used before? Have you come across anything like that before? I'm not going to ask you, but I think you are the only one going again I'm looking at. Maybe you ask this lady.
There is no standard like technology. Still not.
Oh, okay. Have you worked with like sensory data, Internet of Things data before? Have you written a script to collect data? No? Yes, I'm sure you have done. What happens when you collect that data? If you're going to transfer it somewhere else, what do you think is the biggest problem? Probably it's not the semantic, but I'm just asking to see.
Latency, maybe.
Latency, okay. If people are going to process your data, what do you think they need to know about your data? Imagine if you're collecting data from an environment, you deploy sensors here, and you're trying to pass on this data to somebody else, now a third party to use your data. What do you think they're going to do? What they will need? I'm going to walk them, you can't look at your screen.
A description of the data.
Description of the data. What type of descriptions they need? They need to know where you have collected the data, they need to know the location, they need to know what type of information you have collected, this is the temperature, this is humidity, this is noise level, and they need to know what, did I say, location you have collected that data. It's collected from room X, Y, Z. That can be the GPS location of that can be a GPS location, or it can be any type of data, right? That's going to be the topic of lecture today. Having IoT, or Internet of Things, or sensors, we have more and more data. I think for the first time in human history, we have an opportunity to collect data from our planet. You can collect anything about this environment, temperature, people were in this room, the movements, noise. You can capture them, you can store them, and you can play them back and forth. You can create something like a time machine. You can collect all the video data, sound data, everything. You have the technology to do this. And once you've collected it, you can play back, play forth, and we are creating a time machine. Then you can use that data for different type of analysis. But practically, that's what we have. What you collect, you're working with sensory data. You are collecting data with different qualities, with different modalities. When I talk about modalities, I'm referring like the data can be temperature, humidity, noise, different types of data. Some of them are better than the others, some of them more useful than the others. The problem is we collect lots of data, but that data is not necessarily what we want, or is not necessarily in the form we want. And then what we have, the promise of Internet of Things saying, yeah, you have data, you can use it for different purposes, but that's what we have. We have a planet with lots of data, we don't know what to do with it. And the more the scale is increasing, the challenge of what that data is and how we can use it becomes more and more difficult. If you look at the Internet of Things, the waves, how Internet of Things started, the first wave was RFIDs. Then we have tags, and it was pretty simple. You just, the tag's an ID, and you collect it, and you did some reasoning based on different locations, what the tags meant. And the second wave started with sensor networks. We had sensors, devices, that's probably what you're doing for your projects, which collect data, you can program them, you can collect information, and then you can use them for processing. And the sensors, they have their own memory, they have their own processors, you can use that also towards your advantage. The third wave probably was in late, like 2007, 2008. We have lots of, now we have lots of devices, wearable devices, which you can wear, they collect data, different, I won't give examples, your smartphones can collect data. The problem with this is mostly they are proprietary. They collect data for their own purposes. If you buy a product from Nike, from Adidas, from somewhere else, normally they collect sensory data, but that data is fed into their system. Often they are not open. The next wave, which I think is the way we are now, is we have more and more open devices, we have more and more people like you, they start putting devices, program them, collect data, they can publish that data to different places, and then is how to use that data. That becomes important, because it's not just about collecting the data or having the sensors working in an environment, is what we can do with that environment. There are different areas. I'm sure you have attended the summer school, probably you're already familiar. You can use it for health, you can use it for smart cities, so many other applications. What I believe is the future is going to be is we are moving from device-oriented, network-oriented technologies towards data-centric solutions. It means it still is important what you do, the programming, the devices, sensors, everything are crucial, still are important, still we need to improve them, still we need to have better devices, better networks, better computing equipment. But the future is what we can do with that data, right? All the target we do is we are collecting data from environment, and there are different types of data, and it's important what we're going to do with that. Just some examples. You can use it for monitoring the environment, you can use it for energy efficiency, you can for smart grid, for better healthcare, and you can create an infrastructure which other people can come and build smart application on top of what you are providing. That's the promise of IoT data. Again, some examples. It's not only also about the data you're collecting from these physical devices which you program and you do, but there are also more and more trends towards using, for example, social data. If I'm in this room and I'm tuning the temperature, it seems to be 33 degrees Celsius, that's the sensory data. I know there's a quality associated to it, there is a reliability associated to it, but citizen sensing, human sensing is also becoming a part of sensory data information. Then it just, in a very brief, the data we have is multimodal, different types, they are heterogeneous. Each of you, for example, for your projects, I'm assuming you have decided the format to collect your data. Your data can be float, can be decimal. You can decide to associate your data with tags of time, location, how you're collecting it, and probably between different projects you do, you have different agreements how to do it. Then that creates heterogeneity. If you start thinking of, because the idea is we create Internet of Things, and that there won't be an Internet of Things, an Internet of blah blah. There will be one Internet. Just Internet of Things will blend in a few years, this term will disappear as soon as the grant funding disappears for that, and will become only one Internet. And that Internet is an Internet which you have the current tools, documents, web, whatever you have now, and the data from the devices. And as soon as you put the data into the world, you need to know what that data was, where it was collected from, how it was collected, and sometimes your data is noisy, incomplete. I don't know, you have had this problem in your projects you are doing, but often in real-world environments, what you're collecting can be noisy. I can just step over one of your sensors, and suddenly you get completely wrong information. And if you're controlling an environment with that sensor, you have to be very, very careful about that. And data is time and location dependent. When we were publishing documents on the web, when I upload my homepage, I don't care about the time and location. But as soon as I start publishing information about noise level in this room, time and location becomes important. It's important where I collected this data, what time. Because if I say this room is noisy, what time it was noisy? I came 7 a.m., that floor was locked. Then that time defines the importance of that data as well. And then often what happens is the traditional data process, data analytics we had, we used to collect data. If you were doing, for example, data analytics for, let's say, currency exchange analysis, the trend was we collected data, large amounts of it, that's what big data does, and then you process it. But for IoT or for sensory networks, that's not going to happen. What we collect, we need to process it often real time. Because when I say this room is, for example, it's hot, I think it was cold, now it's getting a bit hotter, no, I'm joking. What happens, that data is important now. 10 minutes later, probably that doesn't work anymore. I need to take an action now and, for example, switch on the air conditioning. It means the data can have a historical value for certain circumstances, certain applications, but often you need real-time analysis. Then what you're collecting should be often analyzed or processed in a near real-time fashion. Another thing is security and privacy. It's not my area of expertise. I won't touch much about it, but it's very important because what sensory data collects, if you're collecting data from here, if you're tagging people, for example, these have RFIDs, and you're collecting how people move around, that's my personal information. And you have to be very careful. But I guess that's something we can skip for today, but always keep in mind. Even if you're saying this is anonymous data, it's still public data, is personal data. For example, my boss assumes I'm here today and I'm teaching. If I'm swimming in that swimming pool and you're reporting the location of my location as an anonymous saying the lecturer didn't appear, it's easily, quickly traceable. And that becomes personal data. That's something very important when you're dealing with sensors, you're putting sensors in environments. Even if it's anonymous data, still can be personal. You'll always have this in mind, but that's probably something for future. What happens, what you're collecting is raw data. You're telling me noise level is X decibel, temperature is 35 Celsius. So what? That doesn't give any information, especially to machines. Machines needs part of information, something which they can take an action. As soon as you collect data, you can show impressive diagrams. The I read temperature goes up and down, I read noise level went up and down, you can visualize it. That doesn't worth anything for machines. That doesn't worth anything for the automation. It is worthwhile, it is really useful, but it's to a certain extent. If you keep in a raw level data, still you can't go through the automation process, because Internet of Things, the idea is we create something which can be autonomous, we can have control loops which automatically collect data, take an action, and decide upon it. The raw data often doesn't help. Another thing is, I think I have learned through the experience, often when you have data, you collect lots of data, and many of it often is not useful, and sometimes the useful data is not there. For example, if you want to create a smart room, you might start collecting noise, temperature, and some humidity data, but often I might need, for example, the location data, and it's not there. Then if you're thinking of a real-life scale application, something really deployed, and you deploy and it works, you always have to think what data you need, how you should collect it, and how much of that you need to collect it. Because again, probably you have learned through this week, collecting data is cost energy, cost bandwidth, cost process, and when you're collecting it, you have to decide how much data you want and where you're going to collect it from. And this is a famous pyramid, probably you have seen it. We have data, low level, then if you start creating structure, you create information, but what we are looking for is something which you can take action, actionable knowledge. For example, what we call actionable information is the room temperature has gone up the threshold, switch on the air conditioning, and set the temperature to 27. That's called actionable knowledge. That's something your application can take it and can create a control loop and can act upon it automatically. Then, I'm sorry, but what we have been collecting so far, my understanding has been like maybe raw data, maybe something unstructured, and what we need is to create how we can make that data smart. What I mean by smart data is the type of data which has right semantics. You say where you have collected it from. Where it's collected from, in a format which you can interpret the data, and also provide link and interconnection between different entities which describe your data. That can be location information, time information, type information, and so on. And also you need sometimes the background knowledge. Another thing is, before again I move into semantics, is what is important in IoT data and the sensory data collection. If you have done machine learning, data analytics, or any type of signal processing, data processing, this is like a continuous data, right? That's what happens when you're collecting data from sensors, from IoT environments. And in classic AI, in classic machine learning or signal processing, we have learned this is noise, ignore it. Because if you repeat this process long enough, normally your process will lean towards a Gaussian normal distribution, and that's what we work. Or often we have noise reduction, noise elimination, which takes all this information out. IoT data can be noisy, but often these type of things that we are interested in. It's not, I mean, again, if this was a currency exchange, for example, analytics, you would just ignore it. This was just bad day. But in IoT, that's important. That's where you need to take an action. But you have to make sure this is not noise and this is a real data. Then you need to have some sort of understanding of what that data is, where it came from, with what quality, and so on. Just one more before I move to semantics is if in future or now you're working on data analytics or processing IoT data, what people assume is we collect data from environment and we process them, we create the patterns, and we look at the co-occurrences of patterns. For example, we look whenever people come to this room, we create the patterns and we see the temperature goes high and we take an action. That can be true in a certain extent, but I just wanted to know co-occurrence is not always a causation. It means if two things will co-appear to each other, doesn't mean really one causes the other. Especially with environmental data, if you're collecting, this is just an example. I can just look at number of people checking into their Facebook, and then look at the temperature and find, oh, so many of them are checking into Facebook account and the temperature is also high. There is no relation between that, apart from you might be bored now doing this. But then we have to be careful when we are collecting data and analyzing. If two things co-occur with each other, that doesn't mean necessarily they are causing each other. Another thing is not only about the collecting data, you need to have right infrastructure to describe the data, to store it, to query it, and to analyze it. Probably you have learned this through the week. I'll just skip that. Can you guess what is this? Who can guess what is this?
I think it's the Amazon.
Amazon Cloud?
No. It's a warehouse. Yeah.
It's a warehouse. Yeah, that's a good guess. But it's a different type of warehouse. This is British Library in West Yorkshire in northern England. They have 150 years of newspapers, all published physically in England. And what happens, there is a computer system and there is a robotic arm connected to this. And you request for a newspaper, just a physical one. Of course, not everyone gets the chance to touch them. But if you need any of pieces of like Times of London published 120 years ago, you can request for a digital system and a robotic arm goes and takes it and brings it to you, right? That's a fantastic engineering system. This is something like a matrix by, I think, 5025 by 25 in a big warehouse, yes. But what happens for IoT? You're collecting data, you're running your projects. What happens if I need that data tomorrow? How are you going to collect it? How are you going to describe that data? Where are you going to store it? It's a bit tricky now. Because if you're storing it in a database, the database is very rigid and fixed. And if you're thinking of opening up to others, different people, how should I know what format you have stored it? How should I know you put the value and unit of measurement in different fields, right? That becomes a very tricky thing when you're working with Internet of Things. Then finding the right information from the right place, the right time, and combining different data, it's one of the biggest challenges of Internet of Things. The small-scale projects in a closed environment, if you're writing an application, developing a test bed, a set of sensors for your own purpose, that's fine. But as soon as you start opening it up to people outside your world, it becomes a big challenge. Because simply you might say, temperature is 90 degrees here. That's perfectly correct if you are in Fahrenheit, right? But if I assume my application works with Celsius, if I read 90, probably I would assume that here is on fire, right? And you can completely get the wrong picture, but with just a small piece of missing information can give you a completely wrong picture from your world. Then it becomes important we find a way to describe our data, right? We want to add metadata to our data to say what that data is, and be able to associate, to carry that metadata all through the pipeline when we are communicating our information to third parties. Internet of Things community is not the only research community who had this problem. A long time ago, around 10-15 years ago, the web community had this problem. Because on the web there are lots of information, and they wanted to describe the data in a machine interpretable way. I won't go into detail of semantic web and where it started, and I'll just briefly touch some of the concepts, but mainly in the context of Internet of Things. Imagine this is a very simple scenario of a wireless sensor, and if you have an actuator network, you have a series of sensors, you might have sync nodes or gateways, they connect your information to your backbone network. In our case, we assume this will be Internet, and all this will be part of the Internet. There won't be any Internet of Things anymore, probably in 5 years, hopefully. And then we have the end users, they want to use this information. You already know these devices, they have their own operating systems, they have their own protocols, and energy efficiency, how you process this information, is important in this, right? Do you know all these things? I'm assuming everyone knows about this, right? But what devices, by the way, do you program? What are these platforms? Galileo. It's from Intel. Yeah, Alex is here, okay. And what operating system it runs? Linux. Yeah. Okay. And just give me briefly idea. You're divided into groups. What projects do you do? Let's start with that table.
I cannot tell you.
Oh, it's secret. It's secret. All of them are secret.
They're presenting in the afternoon.
Ah, I see. Is there anything you can reveal what type of data you're collecting? What type of sensors you have on board? Let's ask that table. Just tell me what sensors you have on this gallery here.
We have basic actuators, buttons and a microphone. Basically, what we present is a way for people to interact and reach out for camera. So basically, what type of data we manage is location, a fixed location of the.
You're revealing too much. Be careful there.
So we share the location basically. We share the type of alarm the user is willing to generate, and that location is that information is processed, and then we interact with the user to reach out for as many people as possible to get a fast response or maybe a proper response.
Okay, impressive. Thank you. Thanks very much. And what has been the most difficult part of the project you do? You can tell that, I think, safely. What has been the most difficult thing so far in working with this Galileo? Don't tell about the project, just tell me about this board.
The most difficult part is to find a way how to push on the cloud.
To push on the cloud. Do you have the similar problem? Cables behind it. What is the most difficult part working with this Galileo platform?
It is not really competitive.
You won't tell Alex.
Yes, actually. No, I mean, we have just some problem because it's not really performant like.
All of them are difficult. This is one of the easy ones, actually. Some of them, if you move to work with other operating systems, are even more difficult. Like for my students, we use these tiny sensors. They are even more rigid. This is very luxury. Okay. Do you know about the energy efficiency things? Like if you start doing more sampling, you're using more energy, especially if your device is battery powered, right? If you're pushing too much data into the cloud, especially what you're doing is one hop. You're just directly connected to the backbone network. But if you're something like this, and if your data needs to go through all this to relay this information, if you're battery powered, relying on battery, right? And the more data you push, the more communication. And I'm sure you're aware of computation on that device costs much less than communication. If you're doing, you can do more process on the device before sending it out, is the better because communication uses more power. At least with the technologies we have at the moment, that's the trend. Maybe in future it changes, right? And then we have different protocols. Are you familiar with CoAP, RESTful services? Okay, that's very good. And then if you have CoAP things, you have services which can go directly all through the way to your devices and collect information, right? And this shows you can do some part of the process. You can aggregate data. You can do the processing stuff, sending, for example, the row location data. You can just send the path, for example. Instead of sending the row temperature information, you can send an average temperature for an hour. By doing this, you can save the data. What happens is, as soon as you move out from that project and that 5 people which they know what's happening in this project, if we say that group is going to share data with this group, you need to tell them what format to use for your data. You need to tell, if I collected location data, my location data comes, for example, with the format of longitude, latitude. It's just you switch it the other way around, you're somewhere in Southeast Asia probably, right? Just that simple format, it becomes important. Within this room, probably you can just talk to each other and solve that and make an agreement. Now look at the bigger picture. You're going to share the data with the world. That's what internet is designed for, right? Or with people who have never seen you, who have never known you, but they're going to use your data. You want to be flexible. And for that, you need to have a way of explaining your data, right? What do you think we should do?
Metadata.
Metadata. What type of metadata?
Well, there's also some standards. The IEEE, for example, has the 1451 that specifies how sensor data has to be presented.
That's SenSML, right?
Yeah.
Yeah. Most of this, they rely on XML formats. I can quickly skip in this part. You're more or less familiar. Then you're familiar what Web of Things can be. You just integrate information to the web, and there are some standards. One of them is OGC standards. Have you come across this? OGC stands for Open Geographical Consortium. They were the first people who said, oh, we work with sensors. They're location dependent. They're geographical location. And they created this language called SensorML. It's an OGC standard which explains, and it's based on XML formats, right? Let's keep that in mind. And have you come across this this platform? It's called Zybly. Used to be called PatchPay, right?
Yeah.
Which is an open source. You can write. It has a simple API. You can push your data on the web. If you look at it, this is very interesting and very useful, but designed for humans. This is not designed for machines. Here I can see the location information. You can't read it from here. This is longitude, latitude. These are the tags you say where the data is. And the map clearly shows, for example, this comes from, I can't remember where it is, and this is a temperature and the value of temperature, right? This is very good for human interaction. But the idea of Internet of Things is, can we create something for machines to understand it? You give it this data to a machine. If you're familiar with HTML, if you look at the source, it's just a messy set of scripts. Machines can't make any sense of this data. And as soon as tomorrow, if the PatchPay or Zybly changes this format, machines even will have more difficulties to understand. You can say, I can write a script, go and find this data. But this is very rigid and very fixed way of extracting it. Then what happens, most of the data we create, you publish from your sensors and your devices is designed for human consumption based on predefined semantics that people perceive that information that way. If you look at this, you can guess. Can you guess this is the value, this is the unit of measurement, probably this is the time, some sort of this must be longitude, latitude, right? For us it's not difficult. But you give this to a machine. What happens? How a machine should understand, and that machine is programmed by someone else, somewhere else, another part of the world. How we can tell the machine what this information are, right? As you mentioned, this is very simple. I mean, the technology is there. We can just add some metadata. We add tags to it, right? I create like an XML tag, and I say this is value, this is time, this is unit of measurement, and I share that tags with a third party. Simple, problem solved. They can use that, right? But then, what is all the fuss about this semantics? Part of the fuss is about because we get funding grants, grants for funding for doing projects, doing research, but there are some other problems. You're recording it, so cut that part out. And that's how what happens. You create like an XML document and start sharing that XML document with third parties. And they can use it, they can probably interpret that information. How many of you know about XML? Don't be shy if you know. Okay, then I'll quickly explain a bit about what XML is. XML is a markup language. It just is designed for describing data, providing metadata. It comes with like tags, similar to this part. Then for each data you add like a tag. Then you can say this is a value, this is the beginning and end. That / means end for each. And each tag needs to be closed. And there are lots of tools. Softwares can read and interpret this XML. There are tools you can say, go and find the value tag for me. There are query languages you can say, go in a huge large set of XML documents, go and find all the tags which they have location. And that's also becoming more interesting because if you have large volumes of data, you can collect all their locations. You can call all the values. You can look at all the units of measurements. If some of them are Celsius, some of them are Fahrenheit, you can just simply write a script in 5 minutes and you can convert all of them to the format you want. And normally XML is formed like this. You have just a prologue, which just shows this is an XML document. You have a root element, for example, says this is a measurement, and then you have attributes for that root element. And then you might have millions of these measurements just going down in your document. And as I said, there are different query languages, there are standard forms, lots of open source tools, software, commercial databases, various things you can work with these XML documents, make it easier. And also you can add more details. Here, this is a very simple form. You can even define the data type. You can say, for example, this data type is decimal, and so on. You can say this is float. You can make it even more strict and more definitive. XML is case sensitive. If you just, this is a very important thing to remember. If you're just writing, for example, value, and if you use just a capital V, it's different with completely like small caps. And all of them need to be quoted and closed, all the documents. All right, what happens if you want to tell someone, not giving a sample data, the structure you have decided to share? You want to say, I have a structure which starts with the value, unit of measurement, location, and that item is called measurement. You want to give the third parties the template of your data. You want to share that template. XML community, they have solved that problem. There is a standard way of explaining it. We call it XML schema. XML schema says, just imagine it's like an empty template. It's just, there are no values. You're just sharing the structure of your data. You are saying, for example, I have an element, it's a complex element, it's called measurement, and has these properties, like has a value, has a unit, time, longitude, and you say, what are the data types? And if you share it with anyone, a third party, for example, if now this table designs this XML schema for the data and share it with that table, they can easily understand what format they're going to get data, and they can write their script to process it. And this solves the problem of interoperability to a certain extent, but not to all. And I'll explain what is the problem now after this. Look, this is an XML description of our temperature data. Do you have a temperature sensor on your Galileo? You can use the same format for describing your temperature, right? What happens if that table, you have been quiet so far, uses this format? Is there anything wrong with it? It's the same thing. But now, if you wrote a script which processes this one, you can't read this one, right? And that's the problem. That's the key problem with Internet of Things. It's a very simple thing, but it's very complex to solve. Technology is not the only matter here. Is the agreement is another matter, and it's the way you're going to describe this to people. Because simply, if you have many people publishing different formats of data, easily you will get to that. You can't just go and say, put a gun on people's heads, say, use my format. They will decide to use their own format. How to make sure the format other people use is interoperable with the format. Or everyone will say, my format is the best, come and use my format. But again, you are looking for a global, widely acceptable way of describing it. And that's the key problem with XML. XML is good to describe a document. You can easily put the tags, but you're limited in describing this formality of this tags. What those tags should be called, what should be named. And if you speak different languages, it's just easily, by the way, you can have this is like multilingual. You can use your own language to describe it. It makes it even more complex now. Even people can't read it to understand what you have described. Another thing is, XML is always good to describe a document within itself. But maybe I don't want to have my location described as a value. I want to describe my location is described on Google Maps. Then I want to link it somewhere else. XML has its possibilities to do it, but it's not a very effective way of that. Then everything in XML you describe within the document itself. But often what happens, you need to go beyond. You need to say, my location is not longitude, latitude anymore. I'm just going to describe, like on an open map, where my location is, and I want to link my data to that one. And in XML, it's possible, but it's not easy to do that, and it's not very effective then for further processing. I'll explain it in a minute. Then we can conclude XML provides a surface model. It's always in a tree structure. You have a root element, and you have the features, and then you close it, and you go to the next one. Always like structured like a tree. But what we need often is we need something to be able to explain it like graph. You're familiar with tree and graph models. I don't need to explain. In graph, you can just link any part of the nodes to anything else in another part of the graph, or even external graphs. That's what type of information we need to be able to do. One XML is effective, but it's not an easy way of doing it, or it's not sometimes even it's not possible to do this. And again, in semantic web, they have had similar problems for web documents, and they are using semantic technologies. The idea of semantic web was allowing machines to work in cooperation with people. Here, what we are looking for, we want to make machines to work with other machines in an effective way. We want to have what we call a machine interpretable way of exchanging information. I want you, when you're writing your temperature information, without telling anyone else in this room what you've decided, other people can also collect your data, can read it without coming and asking you how you decided to do it. And how we can do this, probably semantic technologies can help. One of the fundamental technologies which most of the semantic web works uses is called RDF. How many of you have come across this before? Okay, good. RDF is a way of describing graphs. In RDF, everything is a triple, which has a subject, a property, and object. For example, a subject is a sensor. That sensor you are using is my subject. A property has, for example, a manufacturer. That's the property, has manufacturer, and the value of that, for example, for that is Intel. And Intel becomes our object. Then you can easily describe your information in sort of trickles and link them to each other, right? Then we have the Galileo device or sensor device has manufacturer, has sensors. Sensors have values. Sensors have units of measurements, right? You can start creating this graph and add all the properties to describe it. I'll show some examples, make it clear. I won't go into the RDF vocabulary because it just confuses you more, but you will have a copy of the slides, then later on, if you're interested, you can go and read more. Okay, I have 45 minutes. Is that? Yes. All right, slide 36, I have 80. But you should be able to go through. And in RDF, then again, we have an object, we have an attribute, and a value. That's how we organize our information. And again, it can be represented as XML. RDF itself, once you create that graph, you can represent it in XML. Means RDF, description of RDF can still be XML, or it can have different other formats. If you have questions, I'll ask what other formats you can use. But it's not like XML anymore. You have now graph structures. Imagine this is a measurement data. Now I can say my measurement has value. For example, this value is a decimal, has, for example, a time, has longitude, has latitude, and has unit of measurements. And what you're creating here, you are creating a very simple form of what we call ontology. Have you heard this word before, this term ontology? Yeah. The term ontology comes from philosophy. In philosophy, there is one ontology which you describe the universe. Philosophers use the term of ontology to describe the existence of the universe and how different entities in the philosophical world are related. Like many other things, computer scientists hijacked this term from philosophers, and they said, no, we don't have one ontology, we have thousands of them, millions of them. We can create an ontology to describe sensors, we can create an ontology to describe buildings. But the main idea behind an ontology is you have a domain and you want to describe it. And then you start having to say what concepts I have in my domain. In your sensor domain, you have X number of concepts, and you have some properties which link these concepts to their values or to each other. And by doing this, you create like an ontology. This is a very naive and simple type of an ontology which describes the measurement data. And what happens now? You have an instance of it. For example, my measurement 001 has 50 degrees. I can easily see that now it's measured in this time, measured in this longitude, in this latitude, and has a unit of measurement, right? And in RDF, instead of having this, you can say my unit of measurement is defined somewhere else. In NASA's, for example, NASA has this US Space Agency has, for example, a set of ontologies describing all the units of measurements, most the common ones in the world. You don't need to add your data here. You can provide, for example, a link to NASA's ontology. Say, if you want to see what unit of measurement I used, go and see the standard ones. Then what happens, if everyone uses that, then you have a common point of reference, which everyone defines their units of measurement, right? This is simple now. We moved from XML, we created a graph structure, which we can link our data to external data, and we can use it for describing our data. Let's look at now, and this is the way an RDF document is described. Again, if you look at it, the syntax looks very much more or less like XML. Thing is, yeah, these are the properties, these are the values, and this is the main document which we are talking about, measurement one. XML is not the only way you can describe it, but for now, take it from me, let's use XML. Now let's make our structure a bit more complex. Let's add another object. Let's say if you have a location, you might have multiple measurements for that location. If you're sitting in this room for another 2 hours, you don't want to every single time you measure your location, you add this data. You want to create a location object, and every time you do a measurement, call this location 1, and every time you do a measurement, if your location is not changed, just say my location is location 1. And every time I can go to location 1 and find the values, right? You see, now it's becoming interesting. Now you see the advantage of using a graph instead of an XML document, right? Is that clear what I mean by this? You create, like, are you familiar with object-oriented programming things? You create an object, which then you can create instantiation of that object and use it. Our initial structure was something like this. We had a measurement, and we had, for example, a location for this, which was longitude, latitude. But if you're going to take, like, say, every 5 seconds a sample, and if you're going to associate it with data, we already know more data we create is more difficult to handle it, more energy, more bandwidth we need. Then we move towards more structured way. We create a location object. We say this location is longitude, latitude is 50-50, for example, 50-65 or whatever. And if my location doesn't change, I won't send always the location information with longitude, latitude. I say my location is location 1. And what happens now is the same information, I have more structured way of it. And if my measurement 2 has the same location, I just say measurement 2 has location 1026. Right? By doing this, you are creating more structured and more graph. Now, all measurements will point to a location, for example, instance. Interesting thing about RDF is all the resources, they have a URI. If you have a URI, you have a unique identifier. I think that's another big problem. In most of the IoT scenarios, you want to have a standard way of describing a point of reference for each point of data you're collecting. If you use data, more or less, you have solved that problem because everything you describe has a URI. The drawback is it makes RDF descriptions very complex to write because everything has this long URI descriptions. There are some ways around it. And often what happens, you don't really write this RDF. All these XMLs are generated by tools and from scripts and things you have. And you don't need to describe them like opening a notepad and writing them. You don't need to do something like that. And then in XML you have resources. Your objects, your concepts are, for example, sensors, devices, screens. And then they have properties. They have, for example, your screen has a resolution, has a number of characters it can show. Your sensor has a type, it measures temperature, it measures your location. You can add an ID for this. Your entire device can have an ID. You can have a start time for your measurement, end time for your measurement. You can imagine what type of concepts you need. And then you can put them together, create a model for describing your data. But describing data is not enough. You need to be able to have means of collecting that data, querying that data. There is a query language called Sparkle. I won't go into details, but it's a structured query language which allows you to query RDF data and process RDF data. Now let's a little more look into ontologies, because what happens when people start using semantics, when they start thinking, okay, I need metadata to describe my data, they say, okay, I create an ontology. And to create an ontology, as I said, ontology is just a term to describe a domain. You say, my domain is sensors, devices, and you look at what properties your device has, what concepts exist in your domain, and you connect them together. There are tools for doing this. A very common tool is called Protege. Have you used Protege before? It's developed by Stanford Medical School. Interestingly, they were using it for gene ontology, for describing medical terms. And what happens, you open this tool, often there are several other tools as well. You open this tool, and then you start connecting the concept, describing it in RDF, in OWL, and you can generate an ontology. And I go to lots of conferences in the IoT area, and for years and years, probably, Sebastian, you have also come across this, people just create ontologies, countless number of ontologies, and no one uses them. Because it's simple to create, it's difficult to use. Then I try to, in this next few slides, I won't go into detail of really how to create an ontology, how to describe it in Protege. You can just open a Protege, you can download it, install it, and you can use it. I don't think you will have any problem with creating it. I'll try to go a bit more into to the philosophical part of it. What you should do to make sure you're really creating a proper ontology. Before that, I'll just briefly mention there is also something, another language is called OWL. It stands for Web Ontology Language. It's the other way around. Web Ontology Language, but they decided to use OWL abbreviation, probably looks much neater and nicer. And in semantic web, sometimes you need to also add more logic to your descriptions. For example, if you have an ID for your device, you might say, I want to have only one ID, and only one. Or you might say, for example, if my device is manufactured by Intel, can't have any other manufacturer, for example. You want to describe this logically in your model. RDF is limited in doing these things, and OWL gives you a better way of describing more logics into your restrictions, property descriptions, cardinalities, and different things. For example, if you have a unit of measurement, you can just define, say, my unit of measurement can be only Celsius, degree, and that's it. But RDF doesn't allow you. But here, if you use OWL, you can add more restrictions into it. I'll skip that for now to going into details of OWL. Just let's look at what happens. When you have a domain, let's say for describing sensor data, for describing your device, normally you start just looking at it in an abstract way. You say what concepts I have in my model, and then you start describing the relationship between that concept. That's in a very abstract form. If you're familiar with object-oriented, you define your classes and the relationship between classes. Then you come and say, my device is called Galileo number 1. This is an instance of a device. The device was an abstract form. We say device has an ID, has a manufacturer. Now we say Galileo number 1 has a device ID of XXX, has a manufacturer, has an owner of X. Then you divide your data between an abstract description, which is your template description, and individuals, instances. Different texts you might come through different terminology for that. Right? And also, one thing is important, when you design an ontology, when you design a semantic model to describe your data and metadata, it's an iterative process. It's not just you design a model and you put it in the world and you assume everyone will use it. You have to start thinking of, it's not just the device, the tool itself, it's the way how you will let people to produce data with that model. I'll give you more tangible examples of that. How people can query that, where are you going to store this information, how this information can be queried. But these are also important. If you come, let's say one of that groups, for example, one of the groups here says, oh, we are using an ontology, that's how we're describing our data in RDF. None of the other groups won't use that information unless you give them other tools. You say, get this script, run it on your Linux operating system, and you produce data with my format. Get this, you can store it, you can query this information. Then it's not just putting some semantic metadata out there. It also is a more ecosystem of other tools and other APIs, other scripts you give to people to use your information. That's something, at least I have learned through the experience. I have been working in this area for the past 6-7 years. And initially we started putting semantics, designing the models. And I started noticing, yeah, these are good, I can get published, I can get some funding around it. But if those people don't use it, it's just all wasted. And then through the experience we learned, it's not just designing the semantics, it's the easy part. Finding the ways to encourage people, giving the tools, right context, right information for people to use it, to store it, query it, becomes the most difficult part of it. Then if you want to design an ontology, any domain, in this particular context we are thinking of in terms of things, devices, start thinking of what type of concepts you have in your domain. Let's just have a quick look. Take a break of your coding. What type of concepts you have if you want to describe your Galileo devices? What type of concepts? Let's start from here. Device itself. What else you can think of? A device has an owner. Someone owns this. Group A, for example. What else we can hear from you? As a manufacturer is a concept, right? Then we have a concept of device, has another concept of manufacturer, and there is a link between these two. The device as a manufacturer. What other concepts you can think of? Operating system. Device, operating system, and we can link it with as an operating system. What else can we use? Any concept you can think of for this device.
Energy consumption.
This device has energy consumption. An energy consumption unit is per byte, for example. Energy consumption has joule per byte or something. You can have more details about it. Attached sensors. Yes. A device, we have sensors, and there's a link connects this to my device saying this device has sensors or attached sensors. Let's go to the sensor. What properties you can imagine for the sensors? You gentlemen behind us.
Sensor as a measurement unit.
A sensor has a measurement unit. Yes. And a sensor has a type, for example.
Yeah.
What else you can think for a sensor? The sensor is digital or analog.
Calibration information also.
Calibration information. You can say, what are the calibration information? What was the last time you calibrated?
And how many often do you have to calculate that sensor?
How often you need to calibrate this information? You can think more. What else you can add? Let's just go a bit more and think more about this sensor devices.
Well, to which other sensor can correlate to get some different.
What other sensors can correlate? Can I say my sensor has an accuracy, right? The precision, because its accuracy, you can see this one, I think the XXX BTU.
Powering conditions.
Yeah, has a measurement range. For example, what you're measuring as a temperature has a validity range. That's very important, because if you're giving me a temperature information, if I'm going to use it in a different context than your application, I need to know what is the measurement range. If I go 5 meters down the road, is that the data you're giving me is valid or not anymore? Then you have a measurement range, for example. Yeah? By doing this, by thinking of what concepts you have in your domain, and by linking them together, basically you start creating an ontology. Right? There are tools, you can just put these concepts together, define the links, and you click a button, generates the OWL RDF that you want. That's not the difficult part. Is getting the structure is right, and what you need is the most important thing. There are a few more things. Once you do this, now your information is an interoperable format, because you can share that concept, your ontology. You say, that's my world of sensors, that's my world of Galileo, that's how I understand the Galileo for a machine. For my Galileo has an honor, has a device ID, has sensors on board, these sensors has these properties, and you describe it in a machine interpretable way. Then all the groups can get that and can write the scripts to process those tags, right? So it's easy. There are tools, very well-defined tools to tag process them. Then you can say, if someone else now publishing the data, you can easily go and say, find the temperature information, fetch that temperature information out from the data they have described. Then easily you can be interoperable between yourselves and the external world. The problem is, the trap is, often when you do this, is you can easily create a very complex format, right? You can think of so many attributes, so many different things, which often you don't need. For example, for a certain application, for a certain type of scenario, I might need to have this, let's say, calibration information. For many applications, I might not need to have this. Then these are decisions you need to make when you are designing an ontology, a semantic annotation framework for your model. I'll talk a little more about this designing semantic models. But for now, let's look at what else we can do. Once we have the semantic models, now our information becomes more understandable, more interpretable for an external world. If you share that information with someone else, and if you share your model, I can go and find information, I can read how you have measured it, where you measured it, what device measured it. I can do different types of reasoning. I can create more context-aware applications. There are already models for this, which one of the common ones, the only thing is, about this is SensorML, for example, uses XML. And all the limitations I listed for XML applies to to SensorML. Here is XML, it's difficult to link it to outside world, it's more tree structured, and also SensorML is very complex model. There are so many attributes you need to describe. I know you can skip it, but often think of, if you are thinking of an annotation framework, simple. I'll give more examples. Then once you have that, you can also start writing rules. Because if I can fetch the information regarding the location, regarding the values, I can write now rules for my application. And that can be, any of the groups can write such a rule and get data, publish data, get information regarding the devices from any other group. I say, if my temperature, for example, went over 80 Celsius and I detect the smoke, do this. Because these concepts then becomes a standard interoperable way of exchanging data. Easily your rules also becomes interoperable. Then you don't need to go and to speak everyone how you are publishing your data. You're assuming data comes in a structured format and with tags which you can read those tags and interpret those. If you design an ontology one day, if you're using it, always remember, make it lightweight. Through the experience I've learned, it's easy to get carried away with it, create very complex models, which no one uses them, and it's difficult to feed information, and also the complexity makes even the reasoning and other processes more difficult. Always think of compatibility. Designing a model is easy. What other people are going to use it? Who are the users of that ontology? Then you start thinking how to make that more compatible. I'll give you more examples of this, about this compatibility. And modularity. If you're designing an ontology, for example, has calibration, and you think maybe some people won't be interested in this calibration information, why you don't make it in a module? Then you can drop it if someone didn't want, right? Then your ontology becomes modular. You say, these are about the profile of my device, these are about the data of my device, these are about the manufacturer, these are about the data sheet, this is about the maintenance of my device. And you group them. This is a logical way of designing ontology. And then these modules can be added to your description based on a need. You will be surprised. 80–90% of the ontologies I see, they don't have this simple concept. People just design, put everything just like scramble to each other, and then it becomes very complex. A better example, I'll show you an example. We designed an ontology for describing sensors with Worldwide Web Consortium, W3C. If you're familiar, there's an ontology called W3C SSN ontology. I'll show an example of SSN before. I was involved in this. We had people from all the big manufacturers like Boeing, like different companies, environmental agencies all around the world, research institutes, universities, for like 2 years talking and deciding up to simply what concepts we should use to describe ontologies. Once we finished, we published our ontology halfway through. We hadn't finished yet. Alex was designing a testbed for us at University of Surrey, back when he was my colleague. And Alex had deployed this fantastic sensor network we have now at Sensor Testbed, and we have around 200 nodes. Each node has 5 sensors. Multiply it, back then we had around 1,000 sensors. One day Alex just walked into my office and said, "That's brilliant, you work with SSN." I said, "Yeah." He said, "Do you have a model?" I said, "Yeah, we do." He said, "Can you use your model to describe our sensors? I have 1,000 sensors, I want to open it up to other European community, to our external world, to use our sensors to understand what data we publish." I said, "Yeah, how many sensors do you have?" He said, "Well, it's around 1,000. I said, "No, forget about it. This ontology needs like 50 parameters to describe each individual sensor. I don't have a tool to automate this. I need to create these templates, let's say, more or less manually. Each of them takes me 5–10 minutes to do it. If you have 1,000 of it, it will take me like 2 weeks of just work." That's something was very interesting, revelation. We started thinking, it's not what was me. I mean, my other colleagues, they had similar problems when we worked in SSN. We started thinking, just giving an ontology, semantic model, and metadata description model in a small context like your project can be effective. But practically, if you're really thinking of a big, large scale, a big real-world scenario, something you want to deploy and work really, then it's not just a model. You need to think of this lightweightness of your model, modularity of your model, make it easier for people to use, and also you need to give tools to people. You need to give scripts, APIs for people to be able to publish data related to your model. You need to give the tools to people to be able to query that information, to use it, to store it, or at least you need to give best examples of that. And still you will be surprised, like I was in IEEE, I think last week. Again, there were a few papers, people had ontologies putting just this semantic models together. It works very well for the world. But as soon as you start thinking, do you have anyone, or have you thought about anyone else how you're going to use your model? Often the answer is no, we assume people will use it. But how, as often, is the missing point. Just a brief introduction, but when we designed SSN, then we had this in mind, to design something more modular, more lightweight, and we looked at different patterns, which I explained, looking at the existing concepts, deciding the concepts, their relationship, and how they can be linked to each other. SSN, for example, is designed around this module. We have a device, only describe the device. We have a device, this device, for example, measures some data, is deployed in a platform, is a part of a system, can be a more complex system because we had some people from a control background, and you might have some constraints, you might have some measurement capabilities. And then once you have this, you start modeling it through the concepts, how these concepts are related to each other. For example, a device can be a subset of a system, has a measurement capabilities, has a sensing capabilities, and so on. That's through the process of designing SSN structure. And this is a very simplified format of how concepts are related in SSN. And if you see, each box shows a module. For example, if you're not interested in measurement capability, you can just drop that. If you're not interested in describing your deployment, you can just drop that. And it gives you a very abstract form. This just describe your devices, but again, if you want to make it to real world describing, you need to create instances of it, you need to add more details to your description. Again, like any other semantic format, it can be described in an RDF. But RDF is not the only way to serialize it. You can use other formats, other templates. What we didn't describe is still in SSN, which is very important. Once you have a device, once you start describing, let's say you have a semantic model for your Galileo device, and you say my device has a location. My device has the sensor, a sensor has a measurement unit, right? And everyone agrees on this device has a tag called measurement unit, and we know if we read the value for that, we know what measurement unit we have. Still, you have solved part of the problem. The second part, again, which is a very tricky problem, is what happens if people add different values into it. For example, someone can say, my unit of measurement is C, perfectly makes sense. Someone else can say it's Celsius. Someone else can write centigrade. But still, you can read the tag. Your script, your application will read the tag and say this is the measurement unit. But different people might write different things. In different languages, they might write it. And that creates, again, another level of heterogeneity into your data. And that's something, again, you need to think about it to find a way of describing it. One of the approaches is what Web now is using is called linked data. You don't allow people to put strings, open text there. Again, you define a set of taxonomy. You say these are the possible allowed, let's say, unit of measurements you can define. Again, you create an ontology. Now, at least you're familiar with the concept of ontology. You create an ontology of all the unit of measurements you want to describe. And then you say to people, instead of adding C, Celsius, centigrade, or whatever you're adding, go and choose a concept from my taxonomy. If you get to that point of conceptualization in your environment, in your description framework, then you're increasing the level of your interoperability. Let's go back. We started with very raw data, which was just values, comma separated or whatever. We added XML tags. We said, oh, XML tags are not sufficient because people can use different tags. Then we created an ontology. We said ontology defines a common taxonomy for our data. That was interesting. Now we are moving to another level of, we are facing another level of discrepancy here. What happens if people put different values into our terms? And by using other external ontologies, external taxonomies, we can address this problem. If you have questions after this, I'm available. We can talk. Quick thing, because this SSN is used more and more, has become a de facto standard. I just want to say, SSN does not model, for example, the sensor types. It doesn't give you more information about concepts about networking and representation of data or location or other control function. If you are using SSN, you need to think of how to extend your model to include this as well. there is a new one. Again, SSN and HyperCat, I would think they are the most common de facto standards which are being used more and more. And I would think if in future we are going to have a commonly accepted model will be related to one of these two or maybe a combination of these two. HyperCat came from a joint project which was funded by UK's Technology Strategy Board, which Alex was involved, or he still is involved. No? Intel still is in the project. But yeah, Alex was one of the key people who started working in this area. And this is an interesting model. This doesn't use any of the things I said so far. You just dropped all I said. They said, oh, these semantic people are just fucking research. They're not going to do anything useful. We start in a completely different way. And that different way is using JSON. How many of you are familiar with JSON? Yeah? Better. You see, that's why they shifted from RDF to JSON. They said, oh, RDF is complex. People don't use RDF. Let's use JSON. That's very good. Then you know, JSON is an object model. You can use, again, serialized in XML or any other format. You describe your objects and properties. More or less it's the same thing, the concept we can describe the properties. One thing HyperCat has done, which was very interesting, and so far I haven't come across in any of the semantic models, as I said, often people design semantics, they leave it out, they leave it out, they don't think how this information is going to be published, how this information is going to be used. They say, we have a model, it's your problem, go and use it. HyperCat took a different approach. In HyperCat, there is a structure how to use it, how to publish it, how to make sure that the publication way is interoperable. HyperCat works based on assumption you are using HTTP, HTTPS, everything is a service. Imagine you can use CoAP, any HTTP-based services to publish your data. And once you have a URL, you have a directory within URL called cat. If I give you a URL, say this is my service, always if you drop the service name and add a cat, then you're assuming if that service is supporting HyperCat, there will be a directory. Right? Imagine I give you a URL, always you add a cat to the end of URL. If that cat folder existed, this will have a structure like this. And that will be the description of your service. That's brilliant, because then when you are using a census service, when you start using the data from a service, you can always go back as a designer or as a machine script which is programmed to process cat. You can go back, drop the last name, add a cat, and go and read the structure. What happens as soon as this cat exists? If the cat doesn't exist, means that particular resource doesn't support cat description. If that exists, that will have such a structure. Then you will have, based on resources, each resource will have a set of properties. These are described in JSON. But again, that doesn't mean necessarily you can describe it with JSON. You can change it to RDF. You can change it to anything else you want. What cat doesn't have now, cat doesn't give you the schema. Cat doesn't tell you, if you're describing your Galileo, you can say, my Galileo has a link. Go there, cat, I see the description. But what it doesn't tell, if this group uses a different description, and that group uses a different description, still the description won't be homogeneous. Then, if you combine the idea of a cat with the idea of a semantic ontology modeling, resource modeling, and defining the concepts together, probably you get a picture of getting closer to a homogeneous way, to an interoperable way of describing the data. Less and less people looking at me, and they're looking more at their screens. I hope you find it useful. I know you have your projects, but listen to me. Otherwise, I'll walk around. I'll skip this one. Then, once you start having URLs, HTTP formats, and adding semantic description, we are moving now towards more the vision of Web of Things. Doesn't matter what you call it. Some people call it Web of Things. Some people call it Internet of Things, Internet of Everything. Cisco calls it. What do you call it in Intel? IoT? IoT. Yeah. Soon they will create their own term. I mean, but whatever you do, the idea is now how we can integrate this to web infrastructures. Again, publishing this information, making it semantically interoperable solves part of the problem, but still this information needs to be discoverable. You need to have a way of querying this information, finding it. Once you find it, then you go and look at the information which you can provide about things. Could be cat, could be any other type of resource to understand what that properties the object has, and often they are described, need to be described using machine interpretable ways. Just this is a work we did, just a bit of publicity for what we did. This is like a model we have created as a part of a European project called Fiber. Now we have PhiLab, which is for future internet, and this is just an approach of describing data. Here we have semantic models for describing like devices, describing the services, describing the physical world entities. And we have created a template. Here you can use this template to allow people to create instances of your data. What happens, we learned just giving the semantic models is not enough. We have the semantic models, we have published them, it's our URLs, they're available, people can download it, can see how that information be organized. At the same time, we give them a tool which they can create samples of that data. What happens, they can create that sample and then they can use it as a template to add to their scripts to publish more and more data. If you remember, we had a problem I mentioned. What happens if people start, for example, defining their unit of measurement as Celsius, C, or different things. Here we are using some existing ontologies outside, externally available. We don't allow people to describe, for example, their location information as my location is, for example, the University of Surrey. We don't allow them to write University of Surrey. We give them a crowdsourced ontology type of linked data available. This comes from Wikipedia, if you're familiar. Wikipedia is crowdsourced, coming from Wikipedia, has, I think, a few million concepts in it. And some of these concepts are location. Then people choose their location from Wikipedia instead of choosing writing free text. Then as soon as they do that, what happens, because this is like linked data, there are concepts are linked to each other. If you say my location is University of Surrey within Wikipedia, I can go and find other properties. I can go and find, for example, longitude, latitude information. I can find where you are, which country you are, and so on. This is just an example of what happens if you also link your data to external resources. For example, here someone says my location is University of Surrey, and we can ultimately go and find the GPS location, link it on Google Maps, and give all the semantically annotated data regarding the resource. And imagine all this, these are for just matter of visualization, but also practically these are designed for machines. This is just to help users, to designers to understand how to create a semantic model. But practically this all will be transparent to users, and machines should be able to communicate this information and process it. Then just quickly, this is the picture now we have. If you imagine the first picture I showed you had just the sensor networks. Now I've showed a more complex format. You have like 6LoWPAN IP version 6 on your devices. Hopefully Sebastian is here. Let's go through this. All of them, or most of them, may be run IP version 6 in future. Then you have protocols like CoAP, which can provide HTTP level services on your device, or if you don't have it, maybe on your gateway level you will have this. Then these devices publish information to your cloud, to your backend networks. Semantic annotation often can happen within the device level, or if the communication efficiency, the amount of data you communicate is important, then it happens in gateway level. And what happens then, you provide the semantic information data to your end users. Again, something through the experience we have learned is we design lots of semantic models, we publish, we do lots of research in this area. Recently we have realized it's just adding the semantics. Often when we started, we had static semantics. By static semantics, I mean we had a template, like I showed, we published data, we added this information to our template, and we send it out. It's up to people how to use it, how to share it, and we give them all the information and tools. But what we have realized is not enough, because your data, through the way from here to here, gets lots of changes. You collect information, you aggregate it with other data, and you make a decision. For example, you collect traffic information, cars information, you process them, you aggregate them, and here you tell the user there is an accident in road A. Right? For many applications, that's fine. We have now a case, our application wants to know where did you get to this conclusion. How you're telling me there is an accident in road A. And what we're interested to collect the provenance information. I want to know where the information came from. For example, this conclusion you are saying there is an accident could come from social media. We might aggregate the information from social media and say there is an accident. And social media, Twitter can be easily spoofed. 10 of you can publish, there is a fire here, my application will detect there is a fire here. And we have an application wants to know, How did you come to this conclusion? Where did you get this information? And then provenance information also becomes important. Again, if you're interested, I'm running out of time, but we can talk about it. But now in the new models we do, the models are not just static. There are also concepts through the way you can feed information to that. You can say what AI you applied to this, what conclusions you have made, what data has been combined for, how your data has evolved through the pipeline of your process. You don't need necessarily to send all this information to user, but you can link them somewhere, keep them somewhere, and if an application a user wanted, you can always trace back and go and find the provenance information. The more and more, especially environmental data, physical wall data, open data you publish, this provenance becomes more and more important.
Are there any default formats for describing provenance in terms of the data processing that you do?
There is a W3C standard called Provo ontology. Provo.
So you would say, okay, I've done this kind of feature extraction, I've done this type of machine learning technique, or whatever on it,
Yeah, it does. Again, it doesn't give you the vocabulary of the machine learning algorithm, but you can create your taxonomy for that. Like Kerry Taylor, their group, they are using it for fracking. In Australia, like fracking is a big problem. Like the shale gas, they're following the data where it came from. Because companies, for example, they do environmental studies on the fracking, they say this is environmental friendly. But they want to make sure this data is properly collected, is properly combined. What happens, you need the provenance of this information to see. And then, again, just to sum up, your data comes as a raw data. You need to do some pre-processing, take the noise out, aggregate data. You need to add some metadata to your information. Once you have the metadata, then you might start doing some process. For example, find the patterns, aggregate data. Then you might have some semantic interpretation of your data. You add semantics here, but you might have more semantic interpretation of data. And then from that, ideally, you give them actionable knowledge. You will tell me your Galileo device tells me here, for example, now we need to switch on the air conditioning, and that's the conclusion you have got, but this comes with lots of data coming from here. And then with semantics, I can also trace back and see where the data came from, how you come to this conclusion, if that's a part of things you want to describe. Having said that, there are many other things which I don't have time, and it's not in the context of these things to talk about, but there's not just collecting data, adding semantics, there are so many other aspects to this framework. Then in summary, we have lots of data we are collecting. The data often is limited in terms of interoperability. We want to allow users to be able to share data. We want to add semantics and create more structured data. We can then, and also automate this structured data. It's not just creating models, also how to automate this using these models. Then the challenge is we have different devices, different processes, different concepts, how we make sure everyone uses the same models, same concepts. We describe the concept of creating ontologies, defining concepts, making sure the concepts are connected to each other, finding the optimum way, making it modular, and we describe some common ontology models. And often if you're creating a model, it's always good to use existing concepts. If you're going to define a device, probably someone else has done it. And if you start using, for example, SSN device description, you automatically become more interoperable with existing ontologies. That's something is a crucial thing in many ontology designs I see people miss. They create their own model, and you say, when you ask them, but SSN has this model. You say, yeah, but we're still creating our own. If everyone creates their own model, again, you have this discrepancy. The better thing is creating more reusable things, or reuse if someone already has done that. And again, trying to avoid creating ontologies which are expressive enough, but don't make it more complex. They might look good, but it's the important thing is to work for your information. And again, if you can try to use linked data, it means if you're allowing people to add values, if you want to add values to Celsius, centigrade, Fahrenheit to become also interoperable, try to use linked data. Link your data to other information. And again, yeah, if you can borrow terminologies from other models, probably it's better. I just use SSN and HyperCAD, but there are tens of other examples. These are just the most common ones and the ones I have been involved and we have been involved, and I thought they are good examples to show it. Okay, let's get ready. Who is coming to present from Lister? Who is going to present from Lister? Shall we ask this gentleman to present?
Yes.
Yeah, you are. Okay, time's up. Who is coming from this group? Please. Who's coming from this group? Yeah, you go. Quick, we are running out of time.
How should I
Gabriel.
show this? There's no drawing board.
No, just explain what concepts you took.
Okay.
All come here.
Well, basically what I did was to define like logical blocks in which I group some mostly functions based on the type of the use and the components. So basically I have like 4 or 5 big blocks that it interact between between the other blocks is in a user, subscriber, provider approach. So basically what I have is the OS. The OS is the operative system that has its own properties like manufacturer, like version, like type.
And then you have user and subscriber.
Exactly.
Then what attributes do you have for your subscriber?
Well, my subscriber the user can interact with the OS through the touchscreen, the key, the sound voice, the gestures. So that will be the ways the user can interact with the OS layer through the mobile phone.
That's very interesting because once you give the information, then as a programmer, I know what interfaces is there. And if I'm writing a program, I can already pre-plan what interfaces are available and start planning my data for that. I don't need to see the device. I don't need to know about the device. I have the model to describe it. Thank you very much. That was very interesting. Who is next? Yeah. And other groups, you can comment, then we don't spend time. Just quickly, we have 1 minute.
Really quickly, because we define like, we start with the device.
To everyone, not to
we, okay. We define like the device, and
okay.
After we create the blocks, and like the device as operating system.
Has an operating system,
The device has also owner.
Has an owner, you can say who is the owner of the device, yeah.
And this is produced by a manufacturer.
Yeah, you can trace back the manufacturer of the device.
The device has sensor, and this sensor is, the manufacturer produces the sensor.
And each sensor has its own manufacturer, yeah.
The sensor has an observation capability, and this measure value. The value
measures the value,
yeah. And has different aspects like units, accuracy, time, and also
okay,
the value.
each measurement has its unit, measurement, and time. Do you think is there anything we can improve the measurement type of description? Because what happens is this measurement, each measurement has a time, a location, and a unit. What happens if I have 1 million measurements? For each measurement, you are going to add this information? Then maybe you might think, I'm not saying that's the best way. You need to think whether you're adding the unit, location, and things to your device or to your measurements. By changing this, you might significantly change the metadata you're sending out from your device, right? Thank you.
Our design for the smartphone looks like a much normal one with 4 blocks. Is the output, the sensors, the network, and the manufacturer. Is the network has the Wi-Fi and the GSM, and in the output there's a display, the speaker, the vibrator, and the hair jack. And for the sensor, we give the gyroscope.
Yeah, this is interesting because in this design now we have the network specification. For example, we do a project with British Telecom, and they are interested to know when you have a device, you're connected to their network, they want to know what communication facilities you have. Because if your, for example, 3G connection gets broke down, if they know that you have a Wi-Fi, they can offer this service on Wi-Fi.
Yes.
And that type of specification is very interesting.
And Bluetooth.
And Bluetooth, for example. then you know what devices people have, right? Then for different applications, you see different people within this room, they have different focus. You can create a very comprehensive ontologies, but different models, they might have different focuses on that.
Yes.
Okay, thank you. And the last group?
Yeah, basically we have the same as we have already heard. So we have a mobile device which has operating system, which then has the name, the version, the type, and so on. Also we have, it has the manufacturer, who also has the name, and then we have like, has connection interfaces, and these connection interfaces can be several, like Bluetooth, Wi-Fi, 3G, and so on. So it has a battery which has capacity, autonomy, and so on. Of course, it has embedded devices, which is like sensor, who has type, has calibration, has accuracy, has measurement. So the measurement is unit type value. Also, we have like user interface. It's a keyboard. It can be like touch screen or hard keyboard.
And what happens? Do you think if you want to apply this now to a Galileo device, what type of properties can be ported from this? This is designed for a different purpose.
Yeah, probably most of them.
Apart from user interface, maybe a part of the user interface.
Apart from user interface, but also sensor measurement, owner, operating system, manufacturer, communication interfaces.
That's also a good thing. When you're designing an ontology, you already think of what you can create, which is specific to your system, but can be also at the same time generate, which other people can apply for similar devices. Here we talked about mobile device, but Galileo is also another device which you can more or less, they have similarities. Thank you very much. I think all the groups you can get your prizes from SenZations. Thank you very much. And if you have any questions, I'm here this afternoon. Thank you.